on this one, we are just going to set this one up to a point where the rest will just be algebra, mostly because we only have 10 minutes to go. So I'll set up all of the key pieces where the rest of it we would apply our algebra. So on this one, let's start off with our general sketch. Here's the disk. This disk has a mass. It's a pulley with mass. So this disk has a certain mass of 2.5 kilograms. So I'll say mass is 2.5 kilograms. It's attached to a block. The block has a mass of 1.2 kilograms. We have to find the acceleration of the falling block. To me, that seems easy. Oh, that's Newton's second law. So mg for the falling block. Tension going up. Acceleration going down. So let's set up Newton's second law for that. I'm going to put my positive direction. I'm going to define my positive y-axis to just be downward. I'll also define clockwise to be the positive rotation axis. So if I define downward being positive, that says sum of the forces on the mass is equal to the force of gravity on the mass minus force of tension on the mass is equal to the mass times its acceleration in the y direction, which I'll just leave it like that. So force of gravity is mg minus force of tension is equal to ma. Unfortunately, we have two unknowns. We don't know the tension, and we don't know the block's acceleration. But that's okay, because this is what we're trying to find anyway, the block's acceleration. Problem is we need to find the tension. So where do I go to find the tension? We could try and set it up as one system, but the problem is the center of mass of this block is moving. The center of mass of this disk is not. So I couldn't simply use a single equation for Newton's second law because they have different accelerations. So I couldn't use Newton's second law for forces to set it up as one system. Jonathan? Work. Okay, so work would say change of kinetic plus change of potential is equal to the work done. But we don't know how much potential energy has changed because we don't know how far it's fallen. So, and because we don't know how far it's fallen, we don't know, we're not going to be able to find the kinetic energy. So work isn't going to help us.
Can you use torque and the force be the tension?
Let's use torque on the disk, because this is just Newton's second law for forces, but now we got Newton's second law for torques. So Newton's second law for torques, let's focus on the disk. We will say sum of the torques, I'll call this axis O, sum of the torques about axis O for the disk, which I'm using capital M, is equal to, all right, so let's add the tension force in there. And this disk is resting on that guy, so there is going to be a normal force between the disk and this arm there. So this is going to be the torque due to tension, the torque due to that normal force is equal to I for the disk times angular acceleration of the disk. Now I left these out because I need to decide on the signs.
Would the disk also have a gravitational force?
With the what?
Would the disk also have a gravitational
Yeah,
force?
good. So let's add that. Okay. Well, the torque due to tension is going to be the distance tension is from the axis of rotation times the magnitude of the tension force. Here's the axis of rotation for tension. Remember, the axis of rotation is drawn from the radial axis through where the force is being applied. So this is sine of 90 degrees. And because that tension would rotate it clockwise, and I'm defining clockwise to be positive, this will be positive. Now let's do the normal force. So the torque due to the normal force. So that's the distance the normal force is from the axis of rotation times the magnitude of the normal force times the sine. I don't even know what angle that's going to be. And I'll just put gravity here while I'm at it. I left my sines out because I know what's going to end up on this problem. What's the distance the normal force is from the rotation axis?
0.
0. So there isn't going to be a torque due to the normal force. What's the distance gravity is from the axis? 0. So there isn't going to be a torque due to gravity. So in the end, I didn't really need to worry about those signs, but they go to 0 because they are applied at the axis of rotation. So what that means is radius of tension, force of tension, rotational inertia of a disk, we know that is 1/2 mass of the disk, which is capital M, radius of the disk squared alpha. Well, RT is equal to 20 centimeters. So we know this. Oh, let's go ahead and simplify a little bit. Okay, so do we know the force of tension?
No.
No. We know the mass, we know the radius. Do we know the angular acceleration?
No.
No, but that's what we're trying to find along with the acceleration of the block. So let's look at this. This is equation 1, this is equation 2. I see I have 1, 2, 3 unknowns, but only 2 equations. I need a third equation to help us out.
Does the force of tension goes away?
No. Otherwise, how would this rotate? And otherwise, this would just fall in free fall.
How many were the 2 equations?
Does the force of tension go away? Do you mean, can I substitute this in here?
Still.
Is that what you mean?
Yeah, but still.
Yeah, sure, let's do that.
Yeah.
Let's take 2 and substitute it in for 1. Okay, so when we do that, you're going to see that we're still going to get stuck.
Yeah.
Okay, so we still have 2 unknowns.
So can't we take the radius times angular acceleration?
Oh, you said tangential acceleration is radius times angular acceleration? Is that what I heard?
Yeah.
Yeah, perfect. So Akshay is saying, Mel, look at this. Every point on this string is moving with the same acceleration, which means a point right here on the string or a point right there on the string has the same magnitude of acceleration. Oh, and since this point on the string is actually at the radius of the disk, I know that this linear acceleration connects to the angular acceleration. So what Akshay is doing is he's saying, let's let A equals R alpha. So now we have mg minus 1/2 ma is equal to little m a. Oh, and now we can solve this for acceleration. That is 3 halves ma plus, oops, can't do that, doing too many steps. So I'll just move that on one side. Ma plus 1 half ma equals mg. A is then mg over m plus 1 half capital. So that's the acceleration of the block. I'm sorry, yeah, the acceleration of the block. mg, m plus 1 half m. Now that we know the acceleration of the block, we know the angular acceleration is just a over r. So mg over r, m plus 1 half m. That's the angular acceleration. And then the final step to that problem was find the tension. Oh, and you know what? The tension is just this, 1 half mr alpha or 1 half ma. So the tension equals 1 half ma, which is 1 half mg over m plus 1 half m. We could probably clean this up algebraically a little bit. But there we go. I didn't think we would get this far, but look, we got all 3 parts to that problem. Any questions, guys? All right, so I hope you have a good Monday. I will email you. I'm going to email you tonight with some info, and I will see you Wednesday.